In the middle of chapter 14, which, as we talked about when we started, it is fairly big there. Chapter, a lot of stuff in it, a lot of the really conceptual part of the class, type of information that you really do need to understand sort of what's going on in these problems to be able to do them correctly. So you guys talked about weak acids. So hopefully what you talked about. All right, there you go. So remember that a weak acid, just to make sure, hopefully everybody's on the same page here, is really a weak electrolyte. And what that means in solution, it's pretty much going to kind of stay together, but it will break apart a little bit. So I know one of the examples was HF, which is a weak acid. And when it does dissociate into H plus and F minus. And because it's a weak electrolyte, we do get an equilibrium that's set up. And that means we obviously can have an equilibrium constant that goes with it, which is obviously what is referred to as the Ka value, A being for acid dissociation. And it's the same as normal. It is our products over our reactants. And a couple of things, obviously, about Ka. You always want to use it when it obviously is an acid situation. Only weak acids have Ka values. Strong acids do not have Ka values. The reason that is a strong acid will do what in solution? It will pretty much 100% break apart, right? So it's not going to be able to set up an equilibrium in solution. So we do not see Ka values. And later here, we'll talk about Kb values with anything that is a strong acid or strong base, because they really don't set up an equilibrium. So sometimes people will wonder, like, how do I know it's a weak acid or maybe a strong acid? That is obviously a giant hint if you see a Ka value obviously associated with that acid, either in a table or in the problem itself. That is like blinking lights to say this is a weak acid, which means obviously to sort of solve for pH, we do need to do an ice table for this. We do it like a normal ice table with molarity. And we do our X's, we solve for X, we can make the assumption. And again, if it's less than 5% like we've been using, then obviously you could use that assumption. If it's greater than 5%, you do need to go back obviously and solve it somewhere along the way. And if you went through both of those HF examples, the second one, for example, if the concentration was a little bit lower, like 0.05, the assumption did not work. It was like 13% or 16, I don't remember, I'm getting old, but one of the double-digit type percentage of it was too big. And that is important because really the concentration of a weak acid or even a weak base will really determine how much of it will come off. And when we do the assumption, again, if it's not a very big difference, it's okay. So it's kind of like a pizza example. If you have like a brand new pizza, right, you take one slice out, it's not very much of the whole thing that you started with, so not much is missing. And that's the same thing with acids and things like this. If you have a higher concentration and, you kind of make the assumption it's not going to be that much. But if you're starting with a really low concentration, right, and this always happens, right, there ends up always being only like 2 pieces left in the pizza box, right? Nobody wants to take it. But if you do take one piece away from that situation, that is a very big difference, right, from where you started with just the 2 pieces as well. So concentration does play a really big effect in terms of whether or not, for example, that assumption will work. So again, a reminder, make sure you do always check it. It won't always work, but it will work in these situations a really good amount of time. As the Ka value increases, the strength of the weak acid also increases. And what that means is it's pretty much just the basic idea of what an equilibrium constant means. The larger the equilibrium constant value, that means you should have more products. And really the definition of what makes something an acid is the ability to produce basically this guy right here, the H plus concentration or free H plus in solution. So if you have a larger Ka value, that means you should have more products. If you have more products in this situation, you should have more free H plus in the solution, and it does make it a stronger weak acid, just so we're clear on that, a stronger weak acid in terms of comparison to the Ka. It is still way weaker of an acid than a strong acid, because a strong acid, all it has to do is go for a swim. It's going to 100% dump in there a lot of H plus really quickly, and that's why it's, again, a strong acid. Let's see, any questions on any of that stuff there? Just to make sure. Yeah. Okay. All right. Obviously, we approach it the same way with an ice table on these guys, and the major difference is, in a lot of cases, we're looking for pH, so we do actually just go into the pH expression with our H plus concentration, which is usually the X value in these situations. So I think this is where you guys said you left off then, right? So percent ionization is another thing we're going to talk about. Percent ionization, or percent dissociation, is sometimes referred to. It's basically the amount of H plus that is sort of comes off in a weak acid situation or an acid situation. And really the calculation to calculate the percent ionization is actually the calculation we do to check our assumption. So when we check our assumption, we take the X value right that we got and we divide it by what we were going to subtract it from, which is the initial concentration. So to calculate the percent ionization, you take the concentration really of H plus divided by the initial concentration of the acid there, and you times it by 100%. And again, that'll tell you how much basically H plus, or how much the acid really broke apart. And what we see is what I was just sort of explaining a second ago. We do see a difference in percent ionization depending on the concentration of the acid. First off, a strong acid is 100% ionized. It completely breaks apart, which is that green line. But what we do see is, as the acid concentration increases in a weak acid situation, we actually see the percent ionization go down. And again, that's sort of the example I just said. You know, you take with a one piece of pizza, the whole box, it's not that much. But again, if we're starting with a very small initial concentration, that percent ionization is much, much higher, because it's obviously a greater proportion of what you're starting with. And again, that's basically why in some cases the assumption works okay, and in some cases it will not work necessarily exactly right. So let's take a look at this and see how we can kind of use this information to solve for certain things. We have a solution of 8 molar formic acid. It is 0.47% ionized. We're actually, in this case, looking for the Ka value for formic acid. So we could actually approach this very similar to how we would do a normal weak acid problem, which is usually starting with the weak acid. And what we want to do is basically dissociate it. So it's going to drop off our H plus, and we'll make a little formate there. And in this particular case, we could kind of take an ice table approach to sort of see what's happening here. So initially, we see that we have a concentration of 8 molar here for our formic acid. And initially here, nothing going on the product side. We could do our normal change, which is minus X, plus X, and plus X here, bringing us to equilibrium of 8 minus X, X, and X. Now, normally, right, we would go into our Ka expression at this point, which happens to be, in this case, the concentration of H plus times the formate divided by the formic acid there. But obviously, we don't know what that is at this point. So we could put in our values, which would give us X squared divided by 8 minus X is equal to, I'm not sure. So that's really where the second piece of information can come into play and be helpful here, which is it tells us that this acid is 0.47% ionized. So the percent ionization, as we just saw there, is our H plus concentration divided by our HA times 100%. So in this case, we do know the initial concentration of our acid. We also know the percent ionization. So we actually could put it in here. 0.47% is equal to H plus, which we don't know, divided by our initial concentration of the acid, which was 8 molar in this case, times 100%. We could rearrange that and actually solve for the H plus concentration. The H plus concentration would equal 0.47% divided by 100% times 8 molar, basically. And if we do that, gives us 0.0376 molar. Would equal the H plus concentration there. Any questions on that calculation there? So why is this important? So this is important if we now look at our ice table over here. We have now solved for the equilibrium concentration of H plus, which is this guy. And what we do see in this case is at equilibrium, that is basically what X equals, kind of similar to the calculation we talked about this morning. So basically this X here and that X there, and also that X there, they are all the same, right? They are all the same value, which means in this case, they are all 0.0376. Any questions on that? That means now we could do, and again, this is very similar to the calculation in the experiment today. We can now put that 0.0376 into our equilibrium line and get values for everybody. So I'm going to do that, I think, on another page here, or not, wrong way. Let's go that way. So we have for our formic acid, we have at equilibrium 8 minus X, which means we have 8 minus 0.0376. For the H plus, that was X, which means it's 0.0376. And for the formate there, it was also X, I believe. So that is 0.0376 molar. And that means that this guy would end up being 8 minus 0.0376. And we'll call it 7.9624. So by kind of using the percent ionization, we're able to sort of work backwards and figure out the equilibrium concentrations of everybody. Now what's left is simply just to put it into our Ka expression, which would be 0.0376 times 0.0376 divided by 7.9624, going to get us 0.0376 divided by 7.9624, and we'll call it 1.8 times 10 to the minus 4. Any questions on that calculation there? So obviously this is a couple different ways, or one way that you could use percent ionization here. Again, it basically will allow you, if you need to, figure out how much H plus is there, and you could go to your ice table and kind of fill in the information from that. The other one is obviously just kind of like a straight percent ionization, where you figure out what is the percent ionization of a particular acid. Any questions on percent ionization? All right, so we talked about weak acids there. So let's talk about weak bases. Weak bases were kind of similar to weak acids. Now, when we were dealing with weak bases, it's the same idea. They, for the most part, will stay together. They will create an equilibrium, and we can write an equilibrium constant for it, which again is the same as normal. It's our products over reactants, and it is known again as the KB, B for base. And in this situation, it's really important to understand again how to write the reactions. And when you're dealing with weak bases, I know when we talked about weak acids, we oftentimes will kind of leave water out of the equation. When you're dealing with weak bases, it's a really good idea to put water in the equation so you can kind of visually see it's a base, so it should accept the H plus over there. And we are producing hydroxide here, which is OH minus again, which is why it is considered a base in this case. Just like the trend that we see with Ka values, Kb values, as the Kb value increases, the strength of the weak base also increases as well. And that is because, again, same idea, you will have more products at that point, and you will have more free hydroxide in solution at that point, making it a stronger, again, weak base. Much like in the acid situation, a strong base like sodium hydroxide, potassium hydroxide is much stronger, obviously, than these guys because they also will break apart. Same idea, you can recognize it as a weak base if it does have a Kb value associated with it. No strong bases have Kb values associated with it. So that's, again, a good way you can recognize it as a base. The one difference, though, in terms of the problem solving of this, we are still going to use an ice table in a weak base situation. But when you do solve for X, it is not the hydroxide concentration, but it is the OH minus concentration in this particular case. That means you typically got to go the POH route first and then to the pH. So that's, again, a common mistake. People solve for X, they put it into kind of the minus the log part of it, and they think they are directly calculating the pH, but they're actually not. They're calculating the POH, and you guys subtract 14 to get you to the pH. Any questions on that there? Now, there's always a situation that will be coming up here shortly, and then a lot of problems where you maybe need to decide, should I use a Ka or a Kb? And there's a very simple way to determine which one you should be using, and it does revolve around writing the equations correctly. If you write an equation and on the product side you see hydroxide, you definitely should be using a Kb value. If you write the equation and you see on the product side H plus or H3O plus, that is an acid situation, and you should be using the Ka value. So there are certain problems that we'll talk about here shortly where they frankly give you the wrong K value, and you actually need the other one. So it's really important. I know I said it a lot, to be able to write these equations correctly, because it can very much help you with the calculation part of it. There's obviously a table from your book of some Kb values. And again, if you see a Kb value associated with something, definitely going to be a base. So why don't we try one here? Amine compounds have a bad smell. The Kb here for this guy, ethylamine, is 5.6 times 10 to the minus 4. What is the pH of a 0.15 molar solution? So take some time here, work it out. Again, ice table it and see what you come up with. Let's see how we're doing. So a couple of reminders, you should always kind of look in the problem. I can't give you a lot of important information to maybe help you do the math part of it. So if you weren't sure, as soon as I see a Kb value, I do know I'm dealing with a weak base, which also should tell you probably somewhere along the way I'm going to be doing some ice table type of situation that's going on here. So that's kind of where we want to start. We also know from that it is a Kb value. And as we talked about that, in these situations, water is a good thing to throw in, especially with the bases. And even if you're not sure how to get to the other side, if you understand, again, the basic understanding of a base is basically something that will accept an H plus, you then should know that really the H plus should be heading over there to the left-hand side. And frankly, all you need to do is just add that H plus in here. I'm just going to do it at the end. So NH3, and it also is a plus. That water donating the H plus, acting as an acid, is really what will generate us our hydroxide. So again, that is how we get to sort of that equation. And again, it's really important. You see that equation, and that is what you should have on that side. A lot of times people will not know how to write these equations and they'll end up with H3O plus on the other side or something like that, which may not seem like a bad thing, but it is, because when you get done with the calculation, you're going to go, that's my pH, when it really is not. So it's really important to make sure that you get these guys down. We can do our initial ice part here with our 0.15, our nothing and nothing going on there. We could do our change, which would be our minus X, plus X, and plus X, and at equilibrium here, 0.15 minus X, X, and X. Any questions on the ice table, the equation? Yeah. It is. So again, as I think we might have talked about before, it's a really good idea, especially if you're in an ice table and you know that thing is not included. Don't put anything there, because you might want to kind of use the numbers incorrectly later on. So that's why I didn't do anything here with the liquid part. Yeah, because it's definitely not going to go anywhere. Other questions? All right, at this point, we will go into our KB expression, which is our products over our reactants, which in this case looks something like this here. Again, also leaving the water out for the same reason. Substituting in our line here, which would give us x squared over 0.15 minus x, would equal our 5.6 times 10 to the minus 4. We can assume that x is equal to 0. And if you did that, you're going to get a sad face, because it was like 6.1%. And it was a bad assumption here. So again, really important to make sure you do check it. As you can see, it doesn't always work out correct. So that means we do need to kind of go back and solve it another way, which in our case will mean the quadratic way. And if we come back here, we got our x squared, our 0.15 minus x is equal to 5.6 times 10 to the minus 4. We're basically going to multiply everything on the bottom to the other side there. That's going to give us x squared is equal to 8.4 times 10 to the minus 5 minus 5.6 times 10 to the minus 4x. We want to bring everybody back to the one side there. That's going to give us x squared plus 5.6 times 10 to the minus 4x minus 8.4 times 10 to the minus 5 is equal to 0 in this case. Any questions on that there? At this point, we'll go into our x is equal to minus b plus or minus the square root of b squared minus 4ac, I think, divided by 2a. Putting our values in there, looks like we get a minus 5.6 times 10 to the minus 4. Plus or minus, if you do everything inside the square root, I think you end up with something like 3.36 times 10 to the minus 4. And then if you square root it, you end up with a 1.83 times 10 to the minus 2 after doing that. That would all then be divided by 2a, which is basically 2 times 1 in this case. This is going to give us our 2x values like normal. Doing the positive first here, so adding the top and dividing by 2 gives us an x value of 8.87 times 10 to the minus 3 there. Doing the subtracting part will give us a negative 9.28 times 10 to the minus, I think it's 3 as well. I think 3. Obviously, if we look back on our ice table from the previous page there, we are looking obviously for the OH minus concentration, which is equal to X. So clearly the negative number here is not the correct one, because we cannot have a negative concentration. So we do know that. Also really important, the reminder there from the ice table that this value here is the OH minus concentration. Again, not the H plus concentration like it is with a weak acid. That means really we got to do a little POH action there, minus the log of 8.87 times 10 to the minus 3, going to yield us a 2.05 for our POH. So again, just the understanding of what is going on here. You know, if you understand that this is a weak base and for some whatever reason you get to this point and you think this is the pH, it should not make sense to you, right? Because that would be technically an acidic pH if this was the pH. So these are things you want to think about as you kind of go through these problems. Just double check you're on the right page. At this point, we could finish it up by taking the pH is 14 minus the POH, and that is going to give us 14 minus 2.05, and that will yield us an 1195 pH, which definitely is a basic pH and does make sense in this case. Any questions on any of those parts there? So I would say the two main places where people really struggle with these type of problems is getting the equation correctly written. And secondly, sometimes people go quickly on autopilot and they think the POH is actually the pH. So those are two very common errors that people make when they're doing these type of problems. Any questions on any part of that there? So the next thing we're going to talk about is the relationship really between Ka and Kb. As I mentioned the other day, or actually earlier today, there are certain problems that we're going to come across very shortly here where they give you, for example, the Ka value, but you really actually need the Kb value to do the calculation and vice versa. So there really is actually a really nice way that you can convert between Ka and Kb. And if we take a weak acid equation like we have on the top there, and we take a weak base reaction like we have in the middle, and we actually add them together, we basically get water. And we do know the equilibrium constant for water there is Kw. And that is the relationship that we could have. The Ka times the Kb is equal to Kw. And a reminder, the Kw is at 1.0 times the minus 14 number. So this is a really good way and a really quick way that you could convert into the Kb when you need the Kb or the Ka, depending on sort of what is given to you. And this is also what I was talking about a second ago, that if you should, in your confident correct equation, that is where 100% of the time you see H plus or H3O plus on that product side, you definitely should be using a Ka value. And if you see hydroxide on that product side, you definitely should be using a Kb value. So that's a really good way to know that you should be using it. And also, it also gives you a pretty good indication of what the solution should be. If you are producing H plus or H3O plus on the product side, it probably should be in the acidic range in terms of the pH. And also, obviously, if you're creating hydroxide there on the product side, it should be in the basic range in terms of pH. So let's talk first then about actually acid strength and how we could kind of compare acid strength between different types of acids. And when we have an acid that does not contain oxygen, and these are basically your group 7, your HF, you know, your HCl, all the guys that are listed there, HBr, HI. Your indication may be to think that, you know, what you should look at in that particular case is actual electronegativity, right? And electronegativity increases as you go up on the periodic table, and it is the ability of an atom to bring electrons towards itself. So the idea here is what makes something an acid is the ability to basically release that H plus, which means essentially we need to get this H off of that bond basically so it could come off and be released. So in this type of acid, the overwhelmingly thing that we do look at is actually bond enthalpy or bond strength. And maybe you remember bond enthalpy or bond strength when you talked about bonding, and you know, you had to add up all the bonds you broke and all the bonds you made, and you subtract the difference and it gives you the delta H for that reaction based on bond energy. And what we do see is actually the bond enthalpy or bond strength of the HF bond is 568 versus say HI, which is about 298 there. So bond strength actually increases as you go up in that group. So why does that make HF a weaker acid than HI? And it is because if you want to break this bond to release that hydrogen, you got to throw in there 568 kilojoules per mole, as opposed to if you want to break this guy, you only need to toss in there about 298. So it's much easier to break the bond here, which means it's able to release the H plus a lot easier. And that is why it's actually a stronger acid than HF, because it takes a lot more energy to get that hydrogen off. That means in reality, less of it's going to come off, which means it's going to be a weaker acid. So the overwhelming thing that you want to look at in terms of acid strength when you're dealing with this type of acid that does not contain oxygen is it is actually the bond enthalpy. The stronger the bond enthalpy, the weaker the acid. And the lower the bond enthalpy or bond strength, the stronger the acid will be, because it will be able to basically come off a lot easier. So in terms of strength, this is the strongest over here. And that would be the weakest. Any questions on that there? Now, when we are dealing with acids that, and here's just a trend from your book there, it shows the same thing. When we're dealing with acids that do contain oxygen, they are also sometimes referred to as oxyacids because they do contain oxygen. And we look really at one of two things depending on the situation when we're comparing oxyacids to each other. We will sometimes look at the electronegativity, which, as I just mentioned, is the ability of an atom to bring electrons towards itself, again, increasing up and to the right, with fluorine being the most electronegative atom you can have. Or we will sometimes look at the oxidation state, or oxidation number of the element. Oxidation state or oxidation number of the element is, for lack of a better description, sort of the charge the element has in that arrangement in a covalent bond sharing electrons. It is not always the charge we think of for elements when we think about ionic bonds. You know, like for example, chlorine we think of as chloride as -1 always, but chlorine can be minuses, could be +1s, +2s, +3s in an oxidation state because it's actually sharing electrons. So it's not necessarily always sort of, again, the charge we think in an ionic compound when a metal and non-metal gets together, but it can be, but it's a little bit different oxidation state and number. So let's talk about the first situation, which is we have an acid here where the central atom is different, but they all have the same oxidation number. And in that situation, we look at actually the electronegativity. So a reminder of how to do oxidation numbers, and we will see it a little bit later on as well. But pretty much if you want to assign oxidation numbers and oxygen's involved, it is typically always -2, except if it's peroxide, then it's -1. So that's -2, -2, -2 for all the oxygens. Hydrogen's actually +1. When we add up all the oxidation states or numbers, it should equal the overall charge, which in this case is neutral. So it should equal 0 in this case. So that's a -2, -4, -6, +1 is a -5, which means in this situation, the chlorine is actually having a +5 oxidation state or oxidation number. If we look at the bromine over here, it's the same deal, -2, -2, -2, and +1. So the bromine in this case is also having a +5 oxidation number or state in this arrangement. So clearly we can't go by oxidation number in this case because they're both identically the same. So when this situation occurs, which typically happens when this middle guy is different and everybody on the outside is the same, we look actually at electronegativity. And we would look at the electronegativity of the chlorine and the bromine here, and we would see that the chlorine is more electronegative than the bromine. The part of this that is the acid part is, which part here is the acid part of these guys? It is actually this OH bond, yeah? That is the hydrogen that actually comes off. That is basically what is releasing. And when we look at just any OH bond, is that polar or non-polar, that bond? It is a polar bond. Oxygen is more electronegative than hydrogen. It's basically the bond you have in water, right? Which is why water is kind of polar. It's got the OHs on both sides. And that means that really what we have going on here is the oxygen is more negative because really the electrons are kind of heading towards the oxygen side in that sharing, right? And what that's essentially doing at this point is weakening this bond right between the oxygen and the hydrogen, allowing it hydrogen to come off maybe a little bit easier. So what ends up happening in this case when we have chlorine in the next spot is now those electrons are going to be kind of pulled even more closer to the chlorine because it's more electronegative. And what that's going to essentially do is continue to weaken this bond a lot more. And it's going to allow that hydrogen basically to come off a lot easier. So because chlorine is more electronegative than bromine in this case, the HClO3 over here would actually be the stronger acid than the HBrO3 in this particular case. Any questions on that? So if you got the same oxidation state, which again, just quickly looking at two acids basically occur when you got the same setup, center guy is different. The one that is more electronegative in the center there will be the stronger acid because it will allow that OH bond to be a lot more weaker and the H plus to come off a lot easier. Any questions on that there? The other situation that can occur with oxyacids is we actually have different oxidation numbers there on the central atom. And when that situation, what we look at is actually the oxidation number. So when we do have differences in oxidation numbers, we look at that. And in this case over here, just to kind of review it, the oxygen here is -2, hydrogen is +1, that's -2 and +1 is -1, which means in this case, the chlorine is a +1 oxidation state. Oxygen is -2, -2, and +1 for the hydrogen. That's -4 and +1 is -3, which is how the chlorine gets to a +3 here. This is the one we just did, -2, -2, -2, and +1 gets us to +5. And on this last one here, -2, -2, -2, and -2, that's a -8 +1 for the hydrogen is a -7. To balance it out here, the chlorine would end up with a +7 oxidation state. It's really the same idea. Again, looking at that hydrogen-oxygen bond and those electrons heading this way, the bigger positive oxidation state in the middle is going to drag those electrons even further inside and again weakening that OH bond and allowing the H plus to come off a lot easier. So in this particular case, this would be our strongest acid, followed by this guy, followed by that guy, and lastly that would be the weakest of the bunch here with the smaller oxidation number. Any questions on that there? So those are really the ways we sort of compare acids. No oxygen, bond strength or bond enthalpy, stronger bond strength, the weaker the acid. If the acid involves oxygen, if we have the same oxidation number in the center, we look at electronegativity to help us decide. The higher the electronegativity, the stronger the acid. And if we have different oxidation numbers of the central atom, the one with a larger positive oxidation number will be your stronger acid. Again, the whole idea is really simply OH bond and whatever weakens it the most going to allow that hydrogen basically to be popped off a lot easier and make it in a stronger acid. Any questions on acid strength? All right, the next thing we're going to talk about is salts. So as you hopefully know, when we react an acid plus a base, we basically get two things. We get a salt and water that's basically going to occur. Now, the salt's actually an important thing here. A salt is an ionic compound. And in certain cases, the salt that is made will pretty much not do anything. So it'll pretty much be relatively neutral. In certain cases, the salt will then continue on to react. And in some cases, the salt will react with pretty much what else is there, which is water. So in certain cases, we will get a salt and water to react. And this is what is referred to as a hydrolysis reaction. It involves water. And in certain cases, the salt may react with water and produce OH minus, which we would expect it to be basic. And in certain cases, the salt will react with water and produce H3O plus, which we would expect it to be acidic in this case. So how do we know, will something react with water and go through this hydrolysis sort of problem or reaction? It all comes back to a couple of things that we talked about early on in this chapter. The first thing is the relationship between an acid and its conjugate base, or a base and its conjugate acid. If something comes from a strong acid or strong base, is the conjugate partner strong or weak? Any remember? So the answer is it is a opposite relationship. So if something comes from a strong acid or strong base, its conjugate partner is relatively weak. And if something comes from a weak acid or a weak base, its conjugate partner is relatively strong. And that is a really important relationship to understand when we're talking about salts, is that opposite relationship. And what it means in the case of a salt is if it is relatively a strong salt, which it came from a weak acid or weak base, it will go and react with water in one of these situations. So if we end up with a salt that is relatively strong, if you will, it will continue on and react with the water and go through these hydrolysis reactions and produce either more OH minus or more H3O plus, and obviously have an effect on the pH. The other thing that's really important with salts is these are the typical type problems where they actually give you the wrong K values. So it's really important to make sure you understand how to write these reactions and make sure you are using the correct K value, the Ka or the Kb value. If not, this is where that Kw is equal to Ka times Kb actually comes into play when we are dealing with salts that we just saw there, the Ka times the Kb. So again, if you got an OH minus, that is a Kb situation, and that is a Ka situation in these guys. So let's think about neutral salts, for example. Neutral salts are salts that contain alkali metals or alkaline earth metals. That is group 1 or group 2. And if you want to think about it, group 1 and group 2 from the periodic table, as we've talked about, is pretty much where we find our strong bases come from. So things like sodium or potassium, these things are what are considered going to be relatively weak because, frankly, it comes from a strong base. And so something like sodium chloride will pretty much produce sodium ions and chloride ions in solution. And that is a neutral salt. So if we had a salt like sodium chloride, or a solution of sodium chloride, or a salt solution of sodium chloride, which is basically a sodium ion and a chloride ion. If you had to make an educated guess, what acid and base would that salt probably have come from? What do you think the acid would have been? What acid you know of has Cl in it? Hydrochloric acid would be a very good choice there. So this most likely came from hydrochloric acid reacting with a base that has sodium in it, like sodium hydroxide. Yeah. So when you react something like hydrochloric acid with sodium hydroxide, you produce water and this salt, which is sodium chloride, right? As this is a basically double displacement reaction happening, right? These guys going over there. So sometimes with salts, it's really important to think about sort of where it came from. So what we know is it comes from hydrochloric acid, which is what type of acid? Is it a strong or weak acid? It is a strong acid. So as we were just talking about, the hydrochloric acid is pretty much where the chloride comes from. So because the hydrochloric acid is strong, would we expect the Cl minus to be strong or weak? We would expect it to do the opposite, right? Which would be weak in this case. So we would expect this guy to be weak. And what that means in this context of the salt is it is not going to go and react with water, basically. It's fine. It's just going to kind of float around and not do anything. So we don't have to worry about really the chloride part reacting with water and changing the pH. And if we think about the sodium hydroxide, that is a strong base. And that pretty much is where we would get our sodium from. And because the sodium hydroxide is really a strong base, we would also expect sodium ion to be weak as well, which also will mean it will not continue to react with water. And basically, those type of salts are pretty simple. Because none of those guys are going to go through hydrolysis, what we essentially would assume is the pH of that solution would be neutral, and it would be a pH of 7 if we had a solution of sodium chloride, as it is considered a neutral salt, because essentially both parts of that salt come from a strong acid or a strong base. Any questions on that there? Now, let's say we had a different salt like sodium acetate. When we have a salt like sodium acetate here, it would break apart into two things, a sodium ion and an acetate ion, right? So we, again, if we look at this salt, might want to think about where it comes from. So if you had to make another guess here, what acid would sodium acetate come from, you think? I think I heard acetic acid, which again would be a very good choice there. So acetic acid is really where that acid or that part of acetate would come from. And really the same thing as above, that sodium probably came from something like sodium hydroxide. Again, if you did that reaction, it's a double displacement, positive, negative, and we end up with our sodium acetate and our H2O happening here. So now when we kind of think about where things come from, that's going to help us decide, you know, is there going to be any type of hydrolysis reaction happening? Is there going to be any type of that salt that's going to continue to react? Why don't we start with the sodium here? Would we need to worry about the sodium in this case? Did we worry about the sodium above? We did not, because again, just like above, the sodium probably came from sodium hydroxide, which is group 1 on the periodic table, which means it is a neutral salt, which means the sodium here is a neutral salt. It's not going to really do anything in terms of reacting with water. What about the acetate? It came from acetic acid. What type of acid is acetic acid? Acetic acid is... it is a weak acid. And again, if you're not sure, remember there's a list of a few that we talked about, like HCl, HBr, HI, H2SO4, HClO4, HNO3. This is a nice little list of strong acids, yeah? So I don't see acetic acid on that list. So probably a safe bet to assume that acetic acid is most likely going to be a weak acid. So because acetic acid is a weak acid, it is really related to the acetate guy. Will that conjugate partner there be weak or strong in this case? It will be strong. Again, that opposite relationship that's happening here. And what that means is it will now actually continue to react with water and go through a hydrolysis reaction. The other important relationship is to understand if the acetic acid is an acid, the acetate would be the conjugate what? Would it be the conjugate acid or conjugate base? It would be the conjugate base, right? Because it comes from the acid, which means this partner on the other side is the conjugate base. And that's really important because now when we take that acetate, we can now look at our hydrolysis reaction, which is the acetate part, is going to react with water. And by correctly identifying that the acetate came from an acid, it should actually act as a base here when it's reacting with water. Definition of a base is accepting or donating an H+. The base will accept the H+, right? Bronsted-Lowry definition will accept an H+, and it will make acetic acid. And by the way, in these reactions, if you're not sure what it makes, it always makes where it comes from, which is why it's good to know kind of where it comes from. And it will produce hydroxide in this case. So again, really important to be able to write these reactions and equations because it tells us a lot of really important information for the calculation part here. By the way, the calculation part here would be a nice table at this point. If I had to make an educated guess, would this solution be acidic, basic, or neutral? What do we see on the product side that affects pH? What's on the product side? Yeah, OH. So that's OH minus, which means it probably should be basic, yeah? So as soon as I see this, even before I pick up my calculator to do this calculation, I know my pH should end up being basic because I'm generating hydroxide. So again, that's the really importance of understanding how to do these equations because you should know where you end up at the end. And sometimes calculation can go bad for you. It's a good way to check yourself. By the way, if I need to use a K value, what type of K value should I use here? And we should also use a KB value. And again, as I mentioned, these are the ones where they typically, you would be given most likely the Ka value here for acetic acid, which is good in a couple of ways because you see the Ka for acetic acid tells you what it makes on the other side, but you would need to use that Kw to flip it around to the Kb. So really important in this case to understand how to write it. And a lot can be really thought of thinking about where it comes from. So this is an example, as we see here, of basic salts. And basic salts are really derived from the reaction of a weak acid with a strong base. We'll produce a basic salt where the salt will react with water and produce hydroxide in this particular case. Any questions on that there? Now, there's also acidic salts, which can be produced. So for example, I think the one on your handout there is NH4Cl, I believe. So that is ammonium chloride, which breaks apart into the ammonium ion and chloride. So again, thinking backwards about what might be reacting here, what acid would be reacting here, you think, to make the NH4Cl? Yeah, again, here we have the Cl minus, and we would put the H plus back on it, and it would be hydrochloric acid reacting here. What base would be reacting here, you think? Well, we know we're not dealing with this anymore. So what does that sort of look like that we've seen that is a base? NH3, yeah, so ammonia. So here in this reaction, this is the base. So the H plus is actually coming over this way from the acid, going to produce NH4 plus and Cl minus. You could keep it together or break it apart, but that is essentially where this salt comes from. So we could do our same sort of procedure here to determine if anything's going to go through hydrolysis. So we'll start with our HCl. The partner there would be the Cl minus. HCl is what type of acid again? It's a strong acid. So do we need to worry about the Cl minus? Is it going to be strong or weak? It is going to be weak, which means it's really a neutral salt. We don't have to worry about it. The NH3, its partner on this side is the NH4 plus. NH3 is a strong base or a weak base? What does most strong bases have in the formula? Most strong bases actually have in their formula OH, yeah, like sodium hydroxide, potassium hydroxide, and they mainly come from group 1 and 2 on the periodic table. That is clearly not the situation with this guy, right? Which means probably a safe bet that he is a weak base. That means that the ammonium here, which would be his conjugated partner, would be weak or strong. And because it does come from a weak base, it's going to be a relatively strong conjugate acid. And again, that's important. We case now that the NH through the hydrolysis reaction. And again, it's going to be the NH4 plus here reacting with water, which is really the hydrolysis reaction. And again, if you're able to identify that that is the conjugate acid, the definition of an acid is something that will donate an H plus. So we would expect the NH4 to donate the H plus over there. And as I said before, even if you're not sure of that, and you can figure this part out, it comes from NH3, and that's exactly what you make on the other side. Again, it always makes where it comes from in these reactions. And in this particular case, when the water accepts the H plus, you will make H3O plus in this case. First off, any questions on the reaction here? Now, just like above, just writing this equation correctly gives us a lot of information. If I had to guess, the pH of this solution should be acidic because you are producing H3O plus. So as soon as you see that on the product side, you are producing H3O plus. Also tells me when I go to do my ice table calculation, a K, what should be used here? Ka value. Again, in this type of problem, you probably would be given the Kb value here for NH3. And that's also very helpful because in the actual problem, it kind of tells you kind of what it makes. So you can kind of use that information to help you out. So when we have a reaction or a salt that really is generated from the reaction of a strong acid with a weak base, it will produce a salt where part of the salt will go through hydrolysis. It's the part that comes from the weak base, and it will always produce H3O plus in this case, and it will always end up in an acidic type pH, and you should always use a Ka value in this case. Any questions on that there? Now, there is another way that you can sort of create an acidic salt, and there are certain metals, small metals, that have a large sort of positive charge that can go through hydrolysis and become acidic. So something like aluminum that has obviously a +3 charge, and that's a bunch of waters attached to it. So what we got going on there is like our aluminum in the middle, and attached to it is really like 6 waters. I'm just going to draw out one of the waters only. One, two, three, four, 5, and one more up here. So what happens in this situation is it's sort of a complex ion. It's really what happens when we write aqueous next to somebody. But in this situation, just another water that is traveling by will basically take an H plus off of that situation. And the result of that is our water will now become H3O plus, which is the hydronium ion. And it will become acidic. And you may be wondering, wow, that is a lot of craziness that looks in that formula. I don't know, the good or bad news is by the time the semester is over, you know how to properly name that. But up until this point, what we have left is basically 5 waters that are intact. So like 1, 2, 3, 4, 5 waters, nothing happened to it. One of the waters lost an H, which leaves a OH left over, which is what that guy is, right? And then OH is OH minus, so the +3 goes down by a 1 and becomes +2. So that's sort of where all the parts of that comes from in that particular case. But in this application, it really is the H plus or H3O plus is being generated here. And that again is another way that we can produce an acidic salt. A lot of transition metals that have like a +2, +3 type charge, kind of those larger positive charges, can oftentimes go through this and have that occur. Aluminum as well. We do see this occur. Any questions on that there? So if we look at something like this, what would the pH be of a 0.45 molar KCl solution? And let's first talk about this salt, which is KCl. When this salt breaks apart, what does it break apart into? K plus and Cl minus. So the first thing we want to think about is, will any of these things go through hydrolysis? Let's start with the K plus. Will it go through hydrolysis? K plus is found where on the periodic table? Group number 1, right? Group number 1 and group number 2 on the periodic table is typically where we find our strong bases, like potassium hydroxide, which is probably where this guy came from. Potassium hydroxide is a weak or strong base? Strong base, which means the K plus is going to be strong or weak. It is going to be weak. So will it go through hydrolysis? It will not. It's a neutral, right? pH 7 basically. It will not go through hydrolysis. How about the Cl minus? We talked about it a number of times. If we had to guess the acid it came from, it would be hydrochloric acid, right? And that's how we get that salt, is that reaction right there between these two guys. Hydrochloric acid, as we've seen, is a strong acid, which means this guy also should be relatively weak, which means it will not go through hydrolysis, which means even though they give you a molarity, there actually is no calculation that's needed. We would assume that this solution would be neutral in this particular case. Any questions on that there? All right, we will lay it up there, I think, right, for now. Sounds good.